This is the third section of chapter 7, and this is about the paired t-test. Okay, so what's this paired t-test all about? Well, let's say we have two sets of data and we want to see if there is a significant difference between the mean of each set of data. Well, in this case we would use the paired t-test. So we collect two sets of data about different things, maybe reaction time, something like that, and we want to see, well, is there basically a difference between the mean of these reaction times, for example. Then we'd use this paired t-test. Now we'd use this for data that we know or assume is normally distributed. So the data that we collect is normally distributed, and then therefore the differences between the two sets of data will also be normally distributed. And also for data where we don't know the mean and the variance, and n is small, so hence the use of the t distribution. So that's the t part of the t-test. Okay, so in a paired t-test, H0 is going to be that the mean of the differences is 0. Okay, in other words, there is no difference between the means of our two sets of data. And H1 is going to be that the mean of the differences is either greater than or less than or not equal to 0. So there is some difference. Maybe one set of data shows that the mean is greater or the mean is less, or it's not equal to 0. So this could be an increase, a decrease, or a change in the mean. So H0 is always this. The mean of our differences is 0. Now when we work out the differences of each pair of data items, so the two numbers in each column, you'll see them when we do the examples in a moment, becomes our new x. So think about what we did in section 7.2, where we had x and we did our hypothesis test. We now replace it with d, the differences between the data items. So we need to work out the mean of the differences. We need to work out the variance of the differences using an unbiased estimator here. So if you compare it with what we had before, this was just x bar here, this was x squared, this was the mean of x squared from 7.2, and because we're using the t distribution, t is equal to the mean of d minus the mean, the d mean, divided by the standard deviation of d over the square root of n, which is our sample size. Now, because what we've said about H0, this value here is always going to be 0. So it's going to be the mean of d, this value here, always subtract 0. So it's basically just the mean of d at the top here, this value. Example 8. In an experiment to test the effects of alcohol on the reaction times of people, a group of 10 students took part in an experiment. Sounds a bit dodgy. Alcohol and students. The students were asked to react to a light going on by pushing a switch that would switch it off again. The reaction times were automatically recorded. After the students had each drunk 1 pint of beer, the experiment was repeated. The results are shown below. Now I hope these are students that were at university and not any younger. So here we've got our students here, 10 different students. This is their reaction times before drinking the 1 pint of beer, and these are their reaction times after drinking the 1 pint of beer, and here are the differences in the bottom row. So they've been worked out for us. What we need to do is test at the 5% significance level whether or not the consumption of a pint of beer increases the students' reaction times. So we can start with H0 and H1. So H1 is that the mean of these differences is 0, that it had no effect on the reaction times, and because it uses the word increased here, that means that we're expecting the mean to be greater than 0. So n is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means that nu, our degrees of freedom, is going to be 10 minus 1, 9, So it's a t distribution with 9 degrees of freedom. It's a one-tailed test since it's greater than, and this is 5%. So now we can look up the critical value in the table, page 39 of the formula book. Go down to row 9, and the second column, I get 1.833 as my critical value. So I've put that information on a t distribution with 9 degrees of freedom. 0 is the central value, and one-tail test, here's my critical value. So I want to now work out my test statistic and see if it's in this area or not. Okay, so I've typed in these differences on my calculator. I've got the sum of d and the sum of d squared from my calculator. I could in fact actually just write down the mean of d and the variance of d from my calculator, but I'm actually going to do my working based on this. So the mean of d is going to be equal to the sum of d over n. So 1.2 divided by 10, so you've got 0.12. So for the variance, here's the formula here. So I'm just replacing the x's that I would have seen before with d. So that's going to be 1 over n minus 1. So that's 1 over 9, same as the degrees of freedom. And then I'm going to have the sum of d squared, which I've got 0.48 minus n, which is 10, times by the mean squared, so that's going to be 0.12 squared. Just about fit it in there. So we'll work out what that gives us. Right, so that gives me exactly 14 over 375. Written as a decimal, that's 0.373. Looks like the 3 is recurring. Now I could have got this directly from my calculator, and the same with the mean as well. So I didn't have to do these calculations here for the sample variance for the mean using the sum of d and the sum of d squared. I could have got this answer here for the sample variance, and this answer here for my sample mean directly from the calculator. But I just did the calculation here so you can see what's going on. So now we work out our test statistic so we can see whether it's in the critical region or not. So that's going to be the mean of d, which is 0.12, minus the mean of the population, which we've said is 0, there's no difference, that's our assumption in our hypothesis test, divided by, now it's going to be the square root of this fraction divided by the square root of n. So I think I'll write it like this. It's going to be difficult to write like a full fraction over a fraction at the bottom. So it's going to be that divided by the square root of n. So n was 10, so root n. So work out that and see what value we get. Right, that gives us exactly 3 root 21 over 7. Guessing that's not particularly useful if I want to know where this goes on that scale. So pressing the ST button, I have a test statistic of 19639 and so on. So I can see that that value is in the critical region. That would be over here. So let me write my conclusion up here. Okay, so what I've put, and you can word it slightly differently, since this test statistic 1.9639, this value here, is greater than the 1.833, it's in the critical region, or you could say that it's significant, so we reject H0, you can say there is evidence to suggest consuming beer increases reaction time. So obviously you can word that differently, but there needs to be reference to the two values, which one is greater than the other, reference to critical region or significance, reference to accepting or rejecting H0, and then a final sentence which goes back to the context of the question and comments on whether this statement, if there's evidence to prove that this statement is true or not. Example 9. In order to compare two methods of measuring the hardness of metals, readings of Brinell hardness were taken using each method for 8 different metal specimens. The resulting Brinell, I'm not sure if that's how you pronounce it, hardness readings are given in the table below. So here they are, reading A and B for all of these different metals here. Use a paired t-test at the 5% level of significance to test whether or not there is a difference in the readings given by the two methods. Well, the first thing that we need to do is to add another column to work out what those differences are, because that's going to be our calculation for our test statistic. So to work out these differences, we want to see whether it's increased or whether it's decreased and write it down as a positive or negative. So for the first one, it's gone up by 2. The second one has gone down by 1. Third one up by 1. And the one after that's gone up by 3. Then up by 2. This one hasn't changed. This one's gone up by 1. And the final one has also gone up by 1. So now we can start our hypothesis test, starting with H0, which is always going to be that the mean of the differences is 0. For H1, it says the word if there's a difference, not whether there's been an increase or decrease. So H1 is going to be not equal to 0. This tells me I'm going to be doing a two-tailed test, and this will make a difference to the significance level. So I had 8 different metal specimens, so n is 8. For my degrees of freedom, 8 minus 1, which is 7, which means a t distribution with 7 degrees of freedom. And since I'm testing at 5%, it's a two-tailed test, I'll be looking at 2.5% to find my critical values. So from the table, 7th row, 2.5%, my critical value is 2.365. So I'm going to draw my t distribution and just put in my critical value, 0 in the middle, critical values actually. So two-tailed test, each of these areas here is 2.5%, and the values are 2.365 and negative 2.365. So now I'm going to calculate my test statistic and see whether it's in the middle part here, except H0, it's not significant, or whether it falls in either one of the tails, and it is significant, and I'll reject H0. Right, again, I'm going to put these values in my calculator. I'm actually going to write down what the sum of d is and the sum of d squared. Again, I could just get the value for the sample mean and the sample variance from the calculator, but if I type one of these in wrong and I just write down the sample mean and the sample variance without showing any calculation, I'm going to get an incorrect answer. So it's best to write these down and then show your working. So my sample mean, sum of d over n, so that's going to be 9 over 8, that's 1.125. And for my sample variance, that will be 1 over n minus 1, 1 over 7, the sum of d squared, which is 21, minus n, 8, times by the mean, 9 over 8 squared. Now that gives exactly 87 over 56. I'll probably use that in my working. And if I press the SD button, 1.5535, 7, and so on. Right, so now I can work out my test statistic. So that's going to be the mean, 9/8, minus 0. That's going to be divided by the sample standard deviation, so it's going to be the square root of 87/56. So square root 87/56 divided by the square root of n, and n is 8. That gives me 2.5528. There's a few other 8's there. That's enough to tell me that this value here is in the critical region. That's going to be over here somewhere, yeah, on this side. And I had an inkling that it would be in the upper tail because the majority of these differences were positive apart from one. So I was expecting it to be over this side. If I had the majority of differences as negative, I'd expect it maybe to be this side over here somewhere. And if there was a sort of about half and half, positive and negative differences, I'd probably expect it to be somewhere in this acceptance region. So now we can write down our conclusion. So I've written this, you can write something similar. So since our test statistic 2.5528 is greater than our critical value 2.365, we reject 8.0, it's significant, it's in the critical region, and then we can say that therefore there's evidence to suggest that there is no difference in the methods used to give the readings. So you should now be able to do exercise 7C from pages 178 to 179 of the textbook.